Hi, I'm Ananta Raghuraman, a student of Purdue University in the ECE department. Today I'm going to talk about maximum likelihood estimation. It is a lecture done by me. To learn more about lectures, please visit www.projectria.org. The overview of today's talk is going to be, first, I'll start with the review of Bayes' theorem. I'll follow it up with a discussion about the Bernoulli distribution. And then I'll introduce the topic of maximum likelihood estimation. And I'll tell you how you can apply maximum likelihood estimation in case of a Bernoulli distribution. We'll then proceed to a Gaussian distribution. And then we'll talk about how MLE can be applied to estimate parameters of the Gaussian distribution. And then finally, we'll look at when MLE would work and when MLE might not work. Okay, let us begin by reviewing Bayes' theorem. Let us consider an example of tossing a die. So when you throw a die, you might get any one of the following results. You can get a 1, 2, 3, 4, 5 or 6. So let us think of an event where we want to know whether after throwing a die we obtained 2 or not. Let us call this event 1 and let us call an event 2 as the event that when I throw a die I want to know whether I get an even number or not. So E1 would be represented by a random variable x1, which would be 1 if I get 2, and it would be 0 otherwise. Similarly, E2 would be a random variable that's defined by x2, which would be 1 if I get an even number, and it would be 0 if I get odd number. So let me assume that I've thrown the die twice. So if I want to calculate the probability with which I get 2 on the first throw, which means I get x1 equals 1 and I get an even number on the second throw, x2 equals 1. So let me also denote that this happened first by adding another number here. So this would be the first throw and this would be the second throw. So by Bayes' theorem, what we actually can calculate is joint probabilities like this. So a probability like this, where you want to calculate the probability with which 2 events would occur, would be given as probability that x11 would be 1 multiplied by the probability that x22 would be 1 given that x11 is 1. So you can think of it intuitively as assuming that this happened first and then you want to calculate the probability that x22 would be 1 given that x11 already happened. So this together would give you the joint probability. As you can see, this is also equal to probability that x22 is 1 multiplied by the probability that x11 would be 1 given that x22 equals 1. So finally, one last property that we'd like to know is this. When you have two events, E1 and E2, if these two events are independent, then you have probability of E1 given E2 equals probability of E1. Similarly, probability of E2 given E1 would be probability of E2. This is because the knowledge of whether E2 happened or not will not affect the probability with which E1 would happen. That is because E1 and E2 are independent. We will use this later in a slightly modified form. Now that we know what Bernoulli distribution is, let me introduce the topic of a likelihood. So let us assume that I have tossed the coin n times and I have obtained the outcomes x1, x2 up to xn. You may recall that any of the xi's where I equals 1, 2 up to n is either 0 or 1, where 1 represents an outcome of head and 0 represents an outcome of tails. And like earlier, we'll assume that probability of x given mu would be mu to the x multiplied by 1 minus mu to the 1 minus x. So I'm going to introduce another concept. We are going to assume that all the xi's are independent and identically distributed. We denote this by the short term IID. So what independent and identically distributed means is that when I say independent, it means that the outcome of xi is independent of the outcome xj for any I and j from 1 until n when I is not equal to j. This is the independence probability, and the identically distributed means that all of the xi's were sampled from the same Bernoulli distribution. Note that to do a maximum likelihood estimation, you do not require the samples to be IID. The advantage is that IID simplifies the computations a lot. So that is the only reason why we use IID. So let us denote D as a set of outcomes that we already have. Now the likelihood function is nothing but the probability that we have obtained D given that we know what mu would be. Or in other words, this is the probability of getting the outcomes x1, x2 up to xn given that we have sampled from the Bernoulli distribution with parameter mu. So since x1, x2 until xn are independent, this probability is equal to probability of x1 given mu multiplied by probability of x2 given mu, and so on. Now we have likelihood function as product of and as we already know, probability of x given mu was mu to the x multiplied by 1 minus mu to the 1 minus x. So substituting this formulae into our equation 1, we get so this is the likelihood function for the Bernoulli experiment that we have done so far.